Hi, everybody. Hopefully you can hear me. Welcome to, let me just make sure that I got, yep, okay. Welcome back to the class, the summer 2020 Physics 121. I posted a couple of announcements on the Canvas site this morning. You have access to the solutions for the first homework, the second homework are both posted. We're grading the second homework. Hopefully they'll have that back to you within 24 hours. The main thing to keep in mind for the second homework is that's the last piece of material that you're responsible for the exam on Thursday. So anything we did in class yesterday, anything we're doing in class today, anything having to do with the third homework, which is posted, all of that will be for the exam next week. You're only responsible for the stuff that we covered last week and the stuff you did on the homework over the weekend. I really do encourage you to look at the posted solutions. They're written in some detail. They're kind of typeset. It's sort of, the posted solutions are sort of the practical textbook of the class in the sense that it basically delineates how to tackle these important homework problems. And so I encourage you to look at those as part of your study materials. So a reminder, the exam is on Thursday morning at 9:30. And I posted an announcement that indicates that we won't have an active lecture tomorrow. There's the third homework, which normally be due tomorrow at 5, has been postponed. There's a blanket extension for 24 hours. You can turn it anytime before Thursday at 5 p.m. And the fourth homework will be posted sometime before Thursday morning, which will be due on Monday. So those are the announcements for the class. So today we're going to do maybe 2, possibly 3 final examples of contending with Newton's laws. Oh yeah, I realized this is important. There was a video that I posted last night on basically a train box on a frictionless surface. That video somehow got scrazzled by YouTube on the upload. I don't know what happened, but I'll reload it early this afternoon, so you'll have access to it. Sorry that you didn't have it for today. I've rearranged things slightly. You don't need to have seen it for us to do the stuff we're going to do today. Okay, so the first, any questions that anybody has about any logistics, anything about the way the course is going along? I will have office hours today. I'm trying to remember when I've scheduled them for, I think 4:30, but I'll send an announcement, a reminder out after class.
I know you said the one video was not working, but the active class from yesterday is also privated.
Oh, okay. All right. YouTube is not my friend yesterday. Okay, let me make a note. So yesterday's active class is there, but you can't see it for some reason. It looks private. I don't know why. I would never post something private, so I don't know why it's that way. And then I'll reload again so there's just a 20-minute example problem on a train of blocks. So I'll fix those right after class today. Any other questions or concerns for today before we start? So we're right in the meat of the course. This is like, the main stuff. That if you can do Newton's second law problems, you can get through this course. There's no question. So I want to do a problem that is both simple and profound, and it does relate in some sense to the homework that you're working on, but it's also it's a somewhat simpler version of it. So let's make sure we'll get the idea. So suppose I have a problem where I've got so this is the ground, right? Like maybe a paved surface or something like this. And on the ground, I have a truck. So here's my truck. Here's a nice artwork of a truck, kind of a pickup truck or something like this. All right. And the truck is on the ground. So there's the truck on the ground. And also the truck itself, behind the truck is a large wooden crate, a box, we'll call it. And so the box is like this. So this is the mass of the truck is m sub t. and the mass of the box is m sub b, and the truck is the motor is engaged. And there's also a ideal rope that attaches from the back of the truck to the box. And the truck, so the truck is basically dragging the box. And the truck is observed to be accelerating forward with a given acceleration a. So the givens in this problem are the acceleration of the truck, the mass of the truck, and the mass of the box. And I want to figure out what are all the forces on each of the two bodies. So in other words, the usual general problem is find all the forces. Okay, now before I tackle that problem, let me ask a question that is in some sense of the word straightforward, but in another sense of the word illusory. Suppose this was a problem on an exam, and it has been. I've put this problem on exams many times in the past. And usually the first part of the problem asks a simple question. What is the net force on the truck? What is the net force on the truck? Now, here's the thing. You've got two approaches to solving that problem. So one approach is to simply proceed with what would amount to parts B, C, and D, where I ask you to figure out all the different forces on all these different bodies. Calculate the force on the truck. Those forces would include friction and the rope and all of all the various different forces on the truck. Add them all up, and the vector sum of those forces is the net force. That's one way to approach it. But if I ever ask you for the net force, I'm not asking you to sum up a bunch of forces. I'm not asking you to go through the recipe. I'm not asking you to do a free body diagram. All I'm doing is asking you to answer the question, what is the net force? So if I say, what is the net force on that truck? How do you answer? You answer very quickly, and you answer very straightforwardly, because there's one law in physics that I am constantly interested in, and that law is Newton's second law. And Newton's second law says simply that the net force is equal to the mass times the acceleration. Do you know the mass? Yes, it's mt. Do you know the acceleration? A. That is the net force. So if I ask you for the net force, I am not asking you to calculate the net force by summing up all the forces and telling me what all the forces are. That's a waste of time. You have a shortcut. The shortcut is the most powerful law in all of mechanics, which is Newton's second law, which says that if I'm asking for the net force, that's just the mass times acceleration. And this is true regardless of the details of what all those forces are. So that's typically part A to these kinds of problems. What is the net force? So I promise you, I will ask a question like this. What is the net force on some body? And it will be set up in such a way that whatever that body is, you know its acceleration, you know its mass. So all you have to write down is literally F equals ma by Newton's second law. And you're done. That's a 10-second answer. If you spend 20 minutes working on all the free body diagrams and doing all the calculations and adding everything up together to get the total force, in other words, if you never cross this equal sign and you spend all your time doing this business, you have not answered part A. You have not properly answered the question. You have not demonstrated that you understand the concept of Newton's second law. This is the right way to do it. Okay? So I promise you I'll ask a question like this on some exam. Maybe Thursday, maybe a week from Thursday, maybe on the final exam. There'll be some question where I'll say, what is the net force? And you'll be like ready to apply this complicated regime of questions. And all I'm really asking you is, do you know the mass and the acceleration? If you do, just tell me the mass times acceleration. Done. But Newton's second law, done. Don't give me anything else. Doesn't belong there. Questions about that? Everybody clear on that? I'm warning you now. I'm going to give you that question, and about a third of the class, I know this because I've seen it in past history, about a third of the class will say, oh, he wants a net force, so I'm going to add up all the forces. About a third of you will do that, even though I'm telling you now that I'm going to do this and you should look for it. So decide that you're not going to be in the third of the class that makes the mistake of working out all the forces and adding them up to get the net force if I ask for the net force. Decide now that you're going to be in the 2/3 of the class that says, oh, that's just Newton's second law, F net equals ma, and I'm done. Okay. Word to the wise. It's not like I'm going to fool you, but again, you got this hammer of all this. You finally figured out all these different things about free body diagram stuff, but don't use the whole system if you don't need it. But now I'm going to say, okay, we want all the forces. I want to know what they are and which way they point. So again, the system is set up. The happy news is that there's no angle theta here, so I don't have to worry about any of that nonsense. And in this case, the happy news is also that I know the acceleration. So that's great. So let's write that down over here. The acceleration in the y direction is equal to 0, and that's for both of them. And the acceleration in the x direction is equal to a. And since the chuck is pulling the box, they both have the same acceleration. In other words, there's a kinematic constraint that the box and the chuck both have acceleration, which is equal to a. And then I can start writing down the free body diagrams. So I'll do the free body diagrams. Actually, I'll do the free body diagrams. I'll erase the announcements and put them over here. So we have lots of room, comparatively. Here we are. So we'll do a free body diagram of the truck. And a free body diagram of the box or the crate, whatever you want to call it. So the happy news is that we know that there's a weight on the truck, W sub T. There's a normal force on the truck, N sub T. That comes from the ground pushing up. Are there any other forces on the truck?
Yes.
Okay. What are the forces on the truck? So what else is on our free body force menu that we put on? What else do I want to put on? Anybody?
Friction.
Friction. Friction sounds great because there's wheels here and the wheels are turning and there's interacting with the road. And so anytime I've got an object that's on a surface and I haven't told you explicitly it's friction, there could be friction. Which way does the friction point? Does it point to the left or does it point to the right? In this problem. Right. To the right. In this problem, it points to the right. How do you know? Because there has to be some force pointing to the right that's causing this truck to accelerate. So again, I'm going to label that the force of friction on the truck. Okay? Because that's the friction that we've got on the truck. These are all forces on the truck. And then there's finally, the only other thing in contact with the truck is that piece of rope. And that piece of rope is pulling. So there's a force of tension. And it's the only rope in the problem, and it's an ideal rope. So I don't really need to, I could label that the tension on the truck. I could label that the tension on the truck due to the block. But since there's only one rope and there's only one tension, I'm just going to label it T for tension. That makes my life simple. And in this case, there's no need to have a tipped coordinate system. I can have X and Y just tucked there in the corner. So I got my coordinates. So now the box, same kind of story. We've got a weight force here, which is the weight of the box. We've got a normal force here, which is normal force on the box. We've got the rope, same rope, so the same tension, pulling the box this way. And the box is dragging on the ground. Oh, the other thing I have to give you, I'm going to give you two other things. I'm going to give you the coefficient, I forgot to mention this, sorry. I'm going to give you the coefficient of kinetic friction between the box and the ground, which I'll call mu sub k, and I'll give you the coefficient of static friction between the wheels of the truck and the ground, which is mu sub s. So these are all givens too. So there's friction on, in this case, since the box is being dragged, there's friction, and the friction acts so as to attempt to keep the box on the ground without moving. So that means it's basically working backwards. So again, I'm going to label this F sub B. let me point something out. When I do my free body diagrams, I don't make it clear on the free body diagram the type of friction. Right? Clearly, this is being dragged, so it's kinetic friction. And here, as long as the wheels are not slipping and not sliding, which I would tell you, I mean, generally speaking, wheels do not slip and slide on cars and trucks. It's a bad thing if they do. So that means at the point of contact, no slipping and no sliding. It's not kinetic, which is to say it's static friction. Okay. So, but I don't usually label the type of friction, the friction by its type. I don't usually put an F sub K or an F sub S. All I do is I label the friction by the body, because that's all we care about when we're doing the free body diagrams. Okay, so now we're in good shape. We can charge ahead. It doesn't really matter which of these two free body diagrams you want to do first, but it turns out that the algebra will be a little bit more straightforward if I do the truck first instead of, sorry, if I do the box first instead of the truck. And it has to do with what you know and what you don't know, but it doesn't really matter which order. But I'll start with Newton's second law. So now we've got the recipe in pretty good shape. Newton's second law, the y coordinate. So one body, Newton's second law, one body. We'll start with the truck. One coordinate at, sorry, not the truck. I said I was going to start with the box. So let's start with the box. Sorry about that. One body, a box, one coordinate at a time, y. And this is the same problem we've solved over and over again. So, but just for completeness, let's make sure we got it down. So again, every time I write Newton's second law, the next thing I write should be F equals ma, and the F should be body coordinate. So in this case, it's box and the y coordinate. That's the net force on B and the y coordinate. Mass B of the box, acceleration of the box and the y coordinate. Okay, and of course this thing is 0 because the box is not jumping up and down. So I get that n sub b, because I look at this free body diagram, that's the y coordinate. I add the positive n sub b minus w sub b equals 0. So n sub b equals w sub b equals m sub bg. So this is the same problem we've solved about 20 times now. Okay, so that's nice. And then I do Newton's second law, box in the x coordinate. So again, F sub, again, I strongly recommend you don't skip this step. F sub, not the box, the truck. No, box, we're on the box still, sorry. F sub bx equals m sub b times a sub bx. Again, I'll give you lots of partial credit if you get this far and you don't do anything else. So always be sure you've got F equals ma somewhere here if you're applying the second law. So again, we stare at this and we say, oh, this thing is equal to m sub b times a. That's what we, no, not times little a, times big A. We know A. So that's great. And then this over here, we've got basically the tension is pulling in this direction. So the tension minus the force of friction, tension minus T minus F of B equals M sub B times A. And then we ask ourselves, well, what do we know? What do we not know? Well, we know M sub B and A with that friction. Well, we don't know it, but we do know that it's kinetic. So at this point, we say, kinetic friction. Okay, so we kind of make a little note over here that F sub B is equal to mu sub K times N sub B. There we are. So the key issue for this rule for kinetic friction, so this is kinetic friction, is that the subscript on the F and the subscript on the N, sorry, that's a little crowded there, are always the same. Whatever force, whatever surface resulting in this friction, that's this surface here, is the same, the normal force you use is the same surface, right there. If this is F sub B, that's the N sub B. If this is F sub 1, 2, this will be N sub 1, 2. It's always the same index. So I can substitute that in. So in other words, T, well here, let me write it this way so I can color code it, so to speak. T minus, now I substitute this in. I say mu sub K times n sub b. Well, n sub b I've already solved for. That's just n sub b is just m sub b times g, and that's equal to m. Go back to this color. M sub b times a. So the only thing I don't know now is the tension, so I can just write it down. The tension is equal to, I bring this over, and I end up with m sub b, and then I've got two terms that m sub b is multiplied by, so m sub b times mu sub k times g plus a. So now I've got all the forces. Again, this force I've solved basically by saying it's this. So now I've got all of the forces, W, N, T, and F, solved on the box. I'm done with the box. Questions about that? So the happy news here is that by starting on the box, I start with basically everything is unknown and calculable except for the tension, so I just solve for the tension. Okay. So again, I'll post this problem as a practice problem, but let me erase it now. Keep in mind that we've got these things here. Cool. So now we do this Newton's second law on the truck in the y direction. I won't go through it because it's exactly the same thing as we did for the box, and you end up with the result that the normal force on the truck is equal to the weight of the truck, which is equal to the mass of the truck times g. It's the same problem. I won't bother you with the steps because we've already done it. And now we say Newton's second law on the truck in the x direction. So again, F sub Tx, the force on the truck in the x direction, equals to the mass of the truck times the acceleration of the truck in the x direction. So again, this is the right side is just m sub t times a. And the left side, I look at the truck and I have a friction this way and a tension this way. So I have F sub t minus the tension is equal to this. And here is where we you can get into trouble, because if you stare at this and go, oh, that's static friction, and I have the coefficient of static friction mu sub s as a given, and you substitute in for the static friction mu sub s times n, which you've already figured out, you've done the wrong thing. You cannot use the coefficient of static friction for anything useful in these problems as a rule, and in particular, you can't use it to calculate the static friction. It's not true that that the static friction is equal to mu sub s times n. That's a false statement. So the only way to get that friction is to carry on with the problem. So F sub t is equal to, well, happy news is I just bring that over there this way. So that basically means that F sub t is equal to t plus ma, m sub ta. And the good news is that we just worked out what t is. I just erased it here, but let me rewrite it. T is equal to, I can barely see it, m sub b times a plus mu sub k times g, I believe is the answer we had before. So I just substitute that in. So F sub t is equal to m sub b times a plus mu sub kg, all of this closed, plus the m sub t times a. And again, I have the force of friction in terms of a bunch of terms, all of which I know, masses, the coefficients, and accelerations given. And then, of course, it's always nice to check units. So this is a force. That's a mass times acceleration. The coefficient of kinetic friction is massless. is unitless. So that's an acceleration plus an acceleration times the mass is a force in newtons. A mass times an acceleration is a force in newtons. Everything looks good. In other words, the force of friction on the truck has to be enough to accelerate the truck while also providing a counterbalance to the force of tension, which is indicated by this term here. Okay, any questions about this problem? So again, if you have kinetic friction, the kinetic friction, you can use that rule of with coefficient of friction. In other words, kinetic friction, coefficient of kinetic friction, that's a good thing. Use it. Yay, that's supposed to be a happy face. Yay. Whereas static friction, if I give it to you, you should just pick it up and put it down like, you know, a piece of spoiled bread. You don't want to have anything to do with it. It's not going to help you. It's a red herring, so to speak. It's a piece of useless information. So I've sort of tossed your way to tempt you into messing up totally. The only way to get the static friction is to apply Newton's second law and calculate what it is. The same for any other unknown force. Questions? So far, so good? Okay. And I think I have one last problem, which is a Newton's laws problem in this sort of regime to do, and then we'll be basically done with Newton's laws for now. We'll come back to it, of course, when we deal with springs and universal gravity. But for now, for the forces that we have, this will be the last example. Okay, suppose I set up a problem like this. Yeah, let's do that. I'm going to give you a pulley. There's a pulley. Supposed to be nice and round. Maybe it's not perfectly round. And the pulley is physically attached to the corner of for now we'll make this simple, a frictionless surface. No friction on that surface. So it's basically, you know, mounted, glued to this surface like this. And we'll do the following. We will attach a rope, an ideal rope to the pulley, and we'll put a block, and we'll label that block A. And then we'll take another block and put it, attach it to the other end of the rope. We'll label this block B. And then we will make another connection. And we'll make another block. I'm going to keep going here. You can see what I'm up to a little bit. This is block C. Color it in green, why not? And then one more block. There's another piece of rope. I'll color that in dark green. And I'll attach it to one more block, which I'll call block D. So that's the setup. I've got a weight hanging off a pulley. I've got 3 blocks attached. I've got no friction. So that's important. So I don't have to worry about that. And what do I know? I know the masses of all 4 blocks, MA, MB, MC, and MD. And I'm going to label the tensions in the ropes here. We'll call this, we'll for sort of consistency, we'll use a somewhat, again, you can use any notation you want, but I'll be somewhat consistent if I label the tension on this rope. I'll call it T sub AB, which is the tension between A and B. The tension here, I'll call T sub BC. And here, I'll call this tension TCD. And I've set up this whole problem, and I want to know only one thing. One thing. What is T sub CD? What is the magnitude of the tension between these two blocks when I set this all up and I release it at rest? Okay, that's a pretty well posed problem. And again, one of the things I suggest is before you even tackle it, sort of make a mental image of what you think is going to happen. Since A is basically hanging here, there's going to be a tension on that rope, and that rope is going to apply a force on B, which in turn is going to apply a force on C, which in turn is going to apply a force on D. So our expectation is the whole thing will start to accelerate. So there it goes, it's going to start moving in this direction. So that's the direction of acceleration. And then at the same time, this block is going to accelerate, and so on and so forth. All the blocks will accelerate. So I want to come up with a reasonable formal mechanism for keeping track of that acceleration. And the key, which is similar to the problem that I posted on the Atwood machine with the pulley, is that we pick a coordinate system, that corresponds to the kinetic constraint between all of these objects. So the key idea is that if this goes down an inch, this goes left an inch, and so forth and so on. In other words, all of these things move together. Even if they're not moving in the same direction, they move together. So I'm going to pick one coordinate system. I'll pick a coordinate system, and I'll call that coordinate system Z, where Z corresponds to the direction of positive acceleration. So that Z is downward here, and Z is to the left here. In other words, I'm going to pick a coordinate system aligned with the acceleration. And the happy news is that I know all the masses, and I don't know the accelerations, but at least I have a kinematic constraint, which is provided by the pulley and the ropes, which says that the acceleration of block A in the Z direction is the same as the acceleration of block B in the Z direction, which is the same as the acceleration of block C in the Z direction, which is the same as the acceleration of block D in the Z direction, which is equal to, well, we don't know what it is, but I'm just going to call it A, and it's unknown. We got to figure it out. It's not given. So unlike the problem with the truck and the box, here we don't know what the acceleration is. We got to figure it out. Or at least we might have to figure it out. We're not asked explicitly for the acceleration. All we're asked for is that tension. But I'm going to argue that the key to doing this problem is to figure out as quickly as possible what the acceleration is, and then, and only then, quickly determine what the force is on that tension. Okay? So we have this kinematic constraint that I'm going to remember. There's only one A. It points in the Z direction, and I'm going to erase that so I can actually work on the problem. So what is my approach? So again, the longhand way to do it, the surefire, tried and true, you can't mess up, but it will take you a while. Way to solve this is to write 1, 2, 3, 4 free body diagrams, work out the tensions and everything that matters in each one of these 4, solve for all of the forces, all of these tensions, and then write down the answer, because one of the things you finally solve for is the TCD, tension between C and D, and I'm done. But that's a lot of work. It's kind of tedious. Is there a shortcut? The answer is, let's see if we can come up with a system, because we have all these things moving together. Now, one system you might think of trying is all 4 blocks the same. And it sounds tempting to say, oh, A plus B plus C plus D, that's one system. And in fact, there's a certain way of thinking about this problem where if you go in that direction, you might succeed in getting the right answer. But it's a little bit perilous. And the reason it's perilous is because even though these 3 blocks are all moving in the same direction, and therefore I can treat them as one object with one acceleration, even though I've called this acceleration and this acceleration the same, in fact, the forces on this system and the forces on this object are not the same. They don't move together. This moves sideways, this moves down. So I'm not going to define all 4 objects as a system, but there is one system I can define, which is kind of nice. So I'm going to define a system to make this problem as simple as possible, I'm going to define a system which is not this block, but all the rest of the blocks put together. So again, the way I define the system is I kind of make a boundary around every part of that system, including the connecting strings. And that's my system. So the system is defined here as blocks B plus C plus D together. They all move together. That's a nice system. That's perfectly fine. And so once I've done that, I can basically write down a free body diagram for both the system and the block that's not the system. So in this case now, I've got a free body diagram for block A, and then I've got a free body diagram for the system. Okay? So the happy news is these are very simple free body diagrams. So block A, it has a weight down, which is weight A, and it has a temperature up, a tension, and that's tension AB. So I want to keep track of that because it matters which tensions are which. And again, I'm going to use this coordinate system Z down. And then for my system, I've got vertical forces, and they matter if you've got friction. But in this case, I don't have any friction. The only forces I'm really interested in are the horizontal forces. There's no friction in the horizontal force. So the only thing that really matters, the only force that's actually being applied to this system as a whole is that same tension TAB. And now I've defined positive Z in the leftward direction. So again, the big advantage of picking a coordinate system that's lined with your acceleration is that you don't have to worry about negative numbers, about things going backwards, so to speak. So now I've got this simple setup, and I can just do apply Newton's second law. So let's charge ahead and do that. I've got a little bit of space to do it. So we'll say Newton's second law. Let me erase this little bit of dangling there. We know what the system is. So Newton's second law on block A, so I say F sub AZ is equal to M sub A times A sub AZ. Okay, so the happy news here is that there's only two forces. So that's T sub AB, that's the positive, no, sorry, I gotta be careful because in this case, it's the weight that's positive, not the tension. So let's make sure we get that right. So the weight on A minus the tension AB is equal to M sub A times that acceleration, which I'll just call A. And again, I plug in what I know, so I get M sub AG minus T sub A, which I don't know, is equal to M sub A A. A little bit of running crowding out of room there. So I've got this equation with two unknowns, TA and A. And then I can do Newton's second law on on the system, again in the Z direction. Both of these in the Z direction. So I say F cis Z equals M cis times A sub Z cis Z. So the left side is just the masses added up together. So that's MB plus MC plus MD, all of those together, times A. I'm sorry, I've run out of room. And then the only force on this system is the tension, T sub A. C. So again, I've got another equation with the same two unknowns, T sub A and A. So for fun, let me just finish the algebra because it's really simple. And I'm going to erase this here because we all know what's going on there. So I can do the algebra real quick. So this, I just substitute this expression for T sub A. I'm not really interested in this tension, but I would like the acceleration. So I'm just going to substitute in for that. So I get, again, I take equation 1, and this is equation 2, and I plug that into there. So it's just substitution algebra. So I get M sub AG minus that term there, which is M sub B plus plus m sub c plus m sub d, that's the mass of the system, times A is, whoops, what have I done? Oh yeah, that, exactly. That's this thing. That's equal to m sub A times A. So I isolate A and I solve for it. So that means just to make sure we get the algebra right. So that's a minus sign. I bring it back there. So I end up with m sub A, m sub A, all of that, plus m sub B, plus m sub C, plus m sub D, all of that times A is equal to m sub A times G. That's nice. And then I solve for A. So I end up with A is equal to m sub A all over m sub A plus m sub B plus m sub C plus m sub D, right? Because I combine these terms, that A plus B, C, D, all of that is basically, that's multiplied by A, and I got a MAG on this side. There we are. Okay, so I have an expression for the acceleration. It's just equal to the ratio of the mass of A divided by the mass of all 4 blocks times G. So that's great. So now that I've got this, then it's easy for me to calculate any of these tensions. So what's my approach? So my approach for getting the tension, I'm going to erase this. My approach for getting the tension, this is my block D, is that, well, I can work out, again, all the details, but I'm just going to focus on the free body diagram for block B. In other words, I'm going to pick a system where that force that I'm interested in is the only force of interest. So the free body diagram of block B is very simple. It's this point plus that tension, C, T, C, D, and then vertical forces that I don't care about. So the calculation becomes very simple. So if I say free body diagram, sorry, if I say not that, I say Newton's second law, sorry. Let's be clear what we're doing. Newton's second law, block D in the Z coordinate, I get F sub dz equals m sub d, that times the acceleration of block D in the Z coordinate. Well, this thing is just m sub d times A, and this thing is just T sub D. So then T C D is equal to m sub D times A, but A is written here. So it's just m sub D times m sub A times G all over the sum of the masses, m sub A plus m sub B plus m sub C plus m sub D. In other words, our approach to these sort of gang of blocks problems where I'm interested in individual tensions is just to work out the acceleration of the whole system as quickly as I can, the acceleration that applies. And then once I have that acceleration, I can consider calculating a force on any subsystem that involves only the tension I'm interested in. So in this case, the subsystem is simply the block B. Anybody have any questions about that? So you can see it, we're tackling fairly rich problems now with a fair amount of complication going on and using this same recipe that we had before. So let me ask a quick conceptual question. We just worked out the tension TCD, but we didn't bother to work out the tension TBC. We also already calculated PABA. So the only tension we never actually calculated was TBC. Well, let me ask you this. Which tension is greater, TBC or TCD? And how do you know? In other words, I'm going to erase this if that's okay. In other words, I could ask a quick conceptual question, which mimics, again, the homework problem with the trains and everything. I can ask the question, you know, basically I say rank these three forces, TAB, TBC, and TCD. Which one's the strongest? Which one's the weakest? Or are they all the same? And again, if you actually worked out in detail what each of these forces are, and you know the values of all those masses, you could calculate those values and rank them. But that's not what we're trying to do. We're trying to get quickly at a ranking. And we'll start, I think, with the comparison with BC and TD, because that's the easiest way to see it. And the way I like to think about it is just say, okay, what's my favorite law of physics? My favorite law of physics is Newton's second law. And if I say, what's the free body diagram look like for block C? The free body diagram for block C looks like this. There's some vertical forces, which we ignore, but there's a tension. There's the two tensions we're interested in: tension TCD and tension TBC. Those are the only two forces in the horizontal direction on block C. But we also know that that's the z coordinate. What's the direction of acceleration? We know that the direction of acceleration of block C is this way. That is the acceleration of block C. So that means that the net force on block C is in the left direction. That means when I consider these two forces, if this block is going to be accelerating to the left, then this thing has to be greater than this thing. In other words, as soon as I say the block is accelerating to the left, I know that the forces to the left and the forces to the right are the same by Newton's second law. I can say that the tension BC is greater than the tension CD by Newton's second law. The logic of the argument again is I observe the acceleration to the left. That means the net force is to the left. That means that the force, the sum, the vector sum of these two forces is to the left. That means this force has to be greater than that force. Does everybody follow that logic? Notice that the key issue is the acceleration, not the motion. If instead of accelerating, if I was just pulling this at a constant, if I was just basically, you know, had set up an arrangement so that the blocks were all moving at a constant velocity, then the acceleration would be zero. And if the acceleration was zero, then these two forces, that the acceleration was zero, then the net force would have to be zero. And in that case, these two forces would have to be equal and oppositely directed, so they would be equal instead of one being on the other. But since I'm accelerating this way, this force is greater than that force. And likewise, if I'm on this side, if this block is accelerating this way, then it's also true that TAB has to be greater than TBC. So the right way to rank them is TAB is greater than TBC, which is greater than TCD. And you can do that without any calculation at all, just by basically asking yourself, what are the forces on these blocks and which forces have to be greater than which other forces in order to give you the acceleration that you want. Remember, Newton's second law isn't just a way to start off these problems, it's a way to understand conceptually what's going on in the free body diagram and to answer certain questions quickly, which can be done just by considering the net forces on the body. Whew, lots going on. Like I said, we're in the meat of the course. So has anybody have any questions about any of this at this point? I'll leave that up for about 10 more seconds, and I'm going to do one last thing, and I'll call it a day. It's not a problem. It's just set up for Thursday's lecture. Okay. Just going to erase this and do one more thing for the day. So we've done lots of work, lots of grinding through a whole class of problems. We got the recipe down, we got the free bodies down, we got F equals MA. We're doing good. And in fact, if we were going to be pedantic about it, we could argue that we're done for the semester, that everything else is gravy. We got kinematics rather, we've got dynamics. And we can use this to tackle almost any conceivable motion that you would want to deal with in principle. But in practice, even though this looks like a complicated problem, it's really quite constrained. We're treating bodies as point-like objects. We're setting up situations where the accelerations are either known, or if they're unknown, they're constant. And we're not dealing at all with things that are spinning around on their axes. We're, by definition, if we're treating an object as a point, I mean, it can move in a circle, but it can't spin. So if it does spin, it doesn't make sense to talk about it spinning. Like, we don't have wheels or other complicated things going on like that. So we got to set up a framework for dealing with that. So I just want to remind you, before we actually do that, what we're going to try to do. So again, this is, you know, physics 121, which is the field of the study of classical mechanics. General Physics 1, mechanics. Okay? And so this means the study of motion. How do things move? Well, it basically deals with motion. Now, actually break the study of motion into two tracks. How, so we've done this before. So the how is called kinematics. Okay? So what goes over here? Position, velocity, and acceleration. That's in 1D. In 2D, we've got uniform circular motion. We've got centripetal and tangential. So your spirographs and all of this stuff. We got projectiles. We got your I hats and your J hats. All of this is a description of the motion. And here, in terms of why, what are the causes of motion? This field is called dynamics. Right? Please explain why things move. Not show me, not explain the motion, and not show me the motion. Describe it mathematically, but explain what causes the motion. We have one basic fundamental system for explaining that motion, which we call Newton's laws. And when we say Newton's laws, what we really mostly mean is the second law, so far with a little bit of the third law, plus forces, the force menu, and the free body diagrams, and all the fun we've had with that. So in principle, you could figure out everything in how a motion by simply saying, we're going to use kinematics to describe what we're doing, and we're going to use dynamics to figure out what will happen according to Newton's laws, as we specify some set of possible forces that could come into play. So far, we've got 4 forces, but we'll add at least 2 more forces, a spring force and universal gravity. And as long as we've got a prescription for every new force, we could just describe and solve every problem in principle. But it turns out that there's another way of basically doing dynamics. And I alluded to this last time I put this up, but just to remind you, there's an independent conceptual way of dealing with describing the motion, and that's called conservation laws. So these are a set of laws that basically say that the reason that things happen is because that there are these physically calculatable quantities that correspond to universal constants, quantities that even if complicated things happen in the system, the total amount of something doesn't change. The most famous one is energy. So in some sense of the word, the cause of motion can be described as due to energy. So we got to unpack what that word is. And another one, of course, is momentum. And in fact, these are the two we're going to really look at, where momentum is going to be broken down into linear momentum and angular momentum. So here's the thing, here's the good news and the bad news. There's a whole bunch of problems that we can do applying Newton's laws, and you've seen them. But there's a whole bunch of problems where I could write it down where in principle you could apply Newton's laws, but in practice it's really hard to do so because we don't know some of the details. Maybe we don't know the forces. Maybe we don't have rules. We don't have a rule for how that force comes into play in the menu. Maybe the acceleration is not only not constant, but we can't write it down as a function of time. We don't know what it looks like. For some of these problems, if we repose the problem in the context of this alternate scheme, energy and momentum, the problem goes from essentially intractable, solvable in principle, but not solvable in practice, to actually sometimes trivially or easily solved. So that's what we're going to do next, is we're going to look down this path for conservation laws and define the concepts of energy, momentum, and see how they work. So the last thing I want to say, though, before we go down the path is what we're going to do is we're going to take Newton's laws and we're going to do a little bit. I'm not really big on doing derivations in my classes. I'm much bigger on solving problems. But we're going to do a little bit of derivation to basically come up with conservation laws as an alternate way of expressing Newton's laws. And in fact, if we look with any mathematical sophistication, you can demonstrate that the conservation laws can be fully derived. They are basically a derivative, a dependency, an alternate mathematical expression of Newton's laws. You can write these down, and once you've written these down, you can prove that these things follow from that thing. But it turns out that that dependence works either way. It turns out if you start with conservation laws, in principle, you can go back to Newton's laws. And the fun and interesting thing is that the reason we start with Newton's laws in this class is not because they're more fundamental than conservation laws, but because Newton lived first and everybody else came later. It's an accident of history. So you learn this first and you learn this second. There are mechanics courses you could take at universities where the professor has decided for their own reasons to start with this and then go to that. I don't know if that's better, but that's not what we're going to do. We started with this and we'll go to that. So that's what we'll do. We'll look at both the next videos for you to look at for Wednesday and Thursday are starting off with the definitions of energy and momentum, and that's what the homework set will be on for over the weekend. Okay, that will be the next module, module 5. And that's all I've got for today. Anybody have any questions about where we're going, about the homework that's due? Let's see, we have a homework that's due. Technically, the homework is due tomorrow, but I've given everybody a blanket extension for Thursday. So, and as always, I'll have office hours. And if you can't come to office hours, just send me a note about when you can meet me. I've already met with several of you during off times to answer questions and address concerns that you have. Going once. The other thing is just so you know, I tend to front load the course with the content and backload the course with basically doing more work and having students do more work in class. So far you've been mostly sitting there passively watching me work example problems and trying to work those examples on your own in the homework. After this week, starting next week, during the last active sessions, probably every other day, I'll have an in-class exercise for people to do. Basically, a kind of a short practice exam problem. People can work together in groups. We'll set up certain ways of doing certain problems. I'll have a couple of demonstrations. You'll see, it'll be fun. So the class will be, now that we've gotten, I'm trying to say, we're almost halfway done with the course. Hard to believe that. In terms of content, even though we're only 2 weeks into the 5 weeks, I'm almost to the halfway point in terms of the content of the course. So I'm front loading the content so that you get extra time to practice doing problems with more and more content. How can I put it? The real challenge when you learn these laws is not that they're harder than these laws, it's that now you got a problem. Every time I give you a problem, you have to make a decision. Do I use Newton's laws or do I use conservation laws? And making that decision is sometimes challenging and sometimes critical to success. If you apply this when you should apply that and vice versa, the problem goes from being really easy to being really difficult if you don't do it the right way. So that's part of the challenge, is figuring out which of these things to do. It's always harder when you're doing exam problems because you're not working at the end of the chapter where you know, this is the chapter on angular momentum. There must be a problem on angular momentum. You don't know if I give you a problem what the concept is. Okay, anybody have any questions about anything? Anything today? Anything for the homework that's coming up? Any questions about tomorrow? Again, I won't be here at 10:30 tomorrow. So look for posted asynchronous material, but we won't actually be meeting in person tomorrow. We'll go back.
Actually, for the video on the trains, you're going to upload that today, right? Like,
I'm going to upload. That's the first thing I'm going to read. As soon as I'm done today, I'm going to reload the train so that you're all set for the train. And you'll see it's quite similar to what we did with the 3 blocks here. So the 3 blocks is an extension of that, but again, they're connected. They're different problems. So hopefully they'll fit together. You'll go. So I already did that lecture. I just have to reload it.
Yeah.
I will fix the fact that yesterday's active lecture is broken. I will load today's active lecture, which is just now what you're watching. And I will have, I believe, 2 asynchronous materials that I'll ask you to look at before Thursday's active lecture.
Okay.
And then between now and Thursday, you'll have time to do everything from, well, study for Thursday's exam to play around with the laboratory exercise that's coming due to looking at these videos and asking me questions and working the practice problems. Okay?
Okay. Thank you.
Sure. And I think that's it. Otherwise, I'll see everybody on the video and otherwise in person for Thursday's exam at 9:30. And for those of you who have special arrangements, I will check with you. We'll get that sorted out. Talk to you soon.